Hi everyone. I would like to go through this problem on our web assignments problem number 17. So for the first part, battery's connected and current starts to flow through, and it's asking how much energy is delivered in the first 2 seconds. Now, we don't have an equation that tells us how much energy is delivered by the battery, but we do have power. And on our equation sheet, we have an equation for power that is listed. As the derivative of energy with respect to time. So if we manipulate that for energy, it would be the integral of power with respect to time. And we know that power for a battery is I times the voltage. All right, so we're going to take this and put that into that integral, but we don't know the current. So at time equal to 0, the inductor stops all current flow, but then a long time after, we know that it follows Ohm's law. The graph of the current as a function of time for this circuit then looks like this, where it has an asymptote at the maximum current found from Ohm's law. The equation for this type of graph is the Imax times 1 minus e to the negative r over L times t. All right, so it's got to be the 1 minus equation, since e to the 0 is 1, so that's where we end up with our 0 point at time equal to 0. Okay, so we got a lot happening here. We have to take the power equation here, plug it into the integral here, but the I in this equation has to be replaced with that. Now we have to do an integral between 0 and 2 seconds, since it is a variable current. So we can't just use the maximum current in our power equation. The current is changing from 0 to something, so because it has a change as a function of time, we have to do that integration. Okay, so writing that out, I'm going to start there, so that the total energy for the battery has to equal the integral from 0 to 2 seconds. Actually, I'm just going to write t because it would be for any amount of time. And then I'm going to substitute the I equation. Actually, I'm going to put in the power equation right here, which is going to be the voltage times I. Now, I is going to be E over R. So I have E times E over R, which gives me E squared over R. And since that value right there was my E over R times this E right here, I still have to include my 1 minus E to the negative R over L times T. All right, so now we have to evaluate this integral. All right, so first thing is, this is constant, so we can actually pull that out. And now we have the integral of this, right, with respect to time. I forgot my dt. All right. So the integral of 1 with respect to time is t. the integral of e to the negative r over L, we can see from our equation sheet they give us that this is the integral right here. All right, so it is going to be the e to the constant times the variable, ours is time, times the 1 over what that constant is. All right, so minus e to the negative RL, so the constant stays the same, times t, but now we have to multiply by the inverse of that constant, which is going to be negative L over R. Okay, now we have to evaluate that between 0 and t. All right, so constant's still there. E squared over R. Okay, so we're going to plug in t first. All right, so we should be used to this in AP Physics that if we go to any time, even though we have the same variable of time, we're putting t in for t. So really that would be 2, but I want to go through the entire proof without numbers first. So we would actually plug in 2 for t everywhere within that equation. So we're going to plug in t for t. All right, and those two negative signs are a plus, L over R, e to the negative R over L times t, all right, and that's plugging in t. Now we have to subtract the lower limit, which would be minus, plug in 0 for t, which is 0, and then plus, remember this is minus the lower limit, and we get e to the 0, which is 1, times L over R. Okay, so all right, that's our total integration there. All right, now we have to simplify this down a little bit. All right, so we still have our e squared over R. We have our t plus L over R, e to the negative R over L t, minus L over R. Okay, so we see we have a similar factor there, and what we can do, simplify that down a little bit more. Oh no. Sorry, if you need that, you got to go back. Remember, this is still equal to the total energy. All right, so we have e squared over R, t, plus, I'm going to factor out L over R, and I'm left with e to the negative R over LT minus 1. All right, and that would be our final equation for our energy. We plug in 2 for t, and we can get our final answer for the energy. Okay. And whenever you have to figure out how much energy is stored in the magnetic field of the inductor, you have to, again, use the current equation as a function of time, which was E over R, 1 minus E to the negative R over L. Times T, and then substitute that into the energy for the inductor, as well as you could do it for the resistor. However, once you have the energy from the battery and the energy from the inductor, you can actually just subtract those two and get the difference. All right, so there's the problem.